Okay, so have you read this theorem? That is this lemma that fundamental group of Sn is trivial. So is that fine or do you have any problem on that? So shall I go ahead? Yes, say something. So what? So have you read? So if you get, then I don't have to recall, right? Okay, so I assume that you have understood this one.
So please repeat this one.
So I will not repeat now. So I asked too many times.
Uh, I came
Okay,
just now.
I'm way ahead with the next part. Huh. What shall I then start? Right. So we have seen that homotopy of paths, right? So we know homotopy of paths. So now we will define homotopy of loops. Sorry, homotopy of maps. So first of all, so what we take, so here we what we have taken, so we have taken two paths f and g, right? Path means the continuous functions from 0, 1 to x, and it was given that f of 0 equal to g0 and f of 1 equal to g1, and we define a homotopy. Homotopy means some so continuous function ft which satisfy the some conditions, right? Now we define homotopy of maps. So first of all, we take two maps. Say let phi and psi be two maps from x to y. So where x and y are some topological spaces. Okay, right. So first of all, we define homotopy of maps. It is called some So with base point preserving. Base point preserving means so there is a continuous function so if so x cross I to y such that so this is my t time. So when t is 0, that will be my uh, phi x, and when f of x equal to 1, so this is my phi 0, and then it will be phi 1x, and at all the point say x0 comma t for any time it is your y0, where so we can say that if there is a map, so for some fix x0 in x and y0 in y, then we say that
Sir, these two maps are phi and psi, not phi 0 phi 1. What you have assumed earlier.
I have assumed phi and psi.
Yes.
Okay, anyway, I am defining that one. I'm just okay. Sorry. Then because I am writing this notation because I need that one actually. So phi t. Okay. Then we say that phi 0 and phi 1 are homotopic. And here you have to mention that with base point preserving. So actually why we are defining that one? So we are defining this one for some purpose, and later we shall see that this condition we do not need actually. That's mean that base point preserving we do not need that. So we can remove that part. That we will see because of that is for our purpose. We can remove that one. Okay. So that's mean here x and y be two topological spaces, and we say that phi 0 and phi 1 are homotopic if there is a continuous function f such that f of x comma 0, that's mean at time t equal to 0 you have phi 0, at time t equal to 1 then it will be phi 1, and for all other points that's mean for any time t f of x0 t equal to y0. Okay, you can
So
see that. Huh.
are these map are of kind group? We are mentioning here base point.
Right, that is a good point. So why we are writing base point? Actually, no. So the base point means this is just a point for a time being because we are not considering any loop here. Okay, so this is just a function. Base point we are writing here base point preserving because we are actually choosing one base point in both the topological spaces x and y. Actually, we will define loop in later stage, and then that points will be my base point for that loops. Okay.
Yes, sir.
Okay, for an example here, there is no concept of loop. So you can say that. So till now, no concepts of loops. So obviously, right? Because phi is just a function, phi 0 and phi 1 is just a function. Function means just a map from a topological space to another topological space. But for a loop or path, we need the domain should be a interval, right? Because here we do not have that. But we need why we are calling that x0 is a base point, because now we will consider a loop with base point x0. So that is the reason we are calling it is the base point preserving. So instead of base point, you can have another any big set as well. For an example, if you remember now definition of deformation retraction, now you can see you have actually homotopy of maps. Can you just recall the definition of deformation retraction and can you compare it? It is actually a homotopy of maps between a retraction R, right, and identity.
An identity.
Right, and again here it is base point preserving. Now, can you tell me what was the preserving there? That was not only the
A.
base point preserving, right? The whole set A. That is a whole subset A, right? But here we do not need that stronger condition. That's mean deformation retraction is just a part of this. Okay. Good. So now why we are doing that? Now suppose now we call the family of paths that phi t. So we can say
So
that
it's
right.
family of maps.
Oh, thanks. Which is a homotopy between phi 0 and phi 1. Actually, we need lots of notation, so better to write phi 0 and phi 1. In other words, you can say that phi 0 is homotopic to phi 1 via phi t. Right. Now we come to the loop. Now let this. Okay. So belongs to that pi 1 x comma x0. Right, so that's mean we have a loop f. Now what is f my? F is a function from is a part of first of all f is a path from an interval I that is 0 1 to x0 to x, right? Such that f of 0 and f of 1 both are x0. So this is a loop with base point x0. Okay, right. Now what is your phi 0 star f? Now that is just phi 0 compose f and that is pi 1 y comma y0. Now similarly, what is my phi 1 star? So it is phi 1 compose f. Again it is in this. Right, that is a so why we needed that base point preserving because of this. See here it is y0, again it is here y0. Okay. Now can you tell me that now we know that phi 0f now homotopic to phi 1. Can you say that? And can you give me one path homotopy between them?
Phi नहीं नहीं नहीं. Phi t composed with F.
Correct. Just phi t composite. This is just a path homotopy between them. Okay, we can write here it is path homotopy. right? So we have a path homotopy between this and this. And since they are path homotopic in terms of loop, so in terms of class, we will say that this is equal sign, right? This. And more specifically, now you can write, because we know that it is very easy. If you write in this way, then there will be no more confusion. So this is a homotopy class in Y, and this is homotopy class in X. Okay, you can try to practice that. Then actually there will be no confusion will be there. Then. Okay, so that's mean actually. So phi naught star F is same as phi 1 star F, right? And this is true. So this is true for all F from phi 1 x comma x0. Okay, so therefore you can say that phi 1 star is same as phi 0 star. Okay, so if you have a homotopy, if you have a homotopy with base point preserving, then if phi 0 and phi 1 are that homotopy with base point preserving, then we have seen that if phi 0 homotopic to phi 1, then phi 1 star is equal to phi 0 star. Right? So there's these star are same, equal. Now we can define that homotopy of spaces in terms of base point preserving. Okay. So now so this is the condition. So x comma x0 to y comma y0 again say x comma x0. This is the thing. So this is my phi and this is my say psi. Now what is this actually? So this means why we are writing in this way, that's mean phi of x0 equal to y0 and psi of y0 equal to again x0. Okay, now let this map, these are maps, this has that, say phi compose psi, that is identity, no, not identity, we will say this is homotopic to identity. Okay, now we know homotopy of maps, right? Now this is identity, where identity it is in X or Y. This I. What is this map identity I?
Y.
Y. And psi compose phi is again homotopic to Ix. Okay. Now here we are writing that. Right. So we should say that it is. Okay, don't need to show that. Okay, fine. So this is. Now we have seen that in this case. So identity is always base point preserving and this is also base point preserving. And when we are meaning that homotopy, that's when it will be base point preserving. I think it is better to say that. Otherwise, how shall we know it is base point preserving? We do not know that, right? The homotopy is homotopy R base point preserving. Right. Okay, so that's mean whenever we have this homotopy, their map homotopy, so that's mean, and during this homotopy, your x0 should goes to x0 always. Okay, and similarly, okay, now it is for y0. Y0 goes to y0, and whenever you have this homotopy, then during all the homotopy, you should have, that's mean for each t, you should have x0 goes to x0. That's mean they are base point preserving. And we have seen that from the previous para, if they are base point preserving homeomorphism and they are um, right, if they are homotopic, then their star are equal, right? Now that imply phi star compose psi star, which is just phi compose psi that star equal to this star. And right, so phi star and these are also identity. Right, now these are also identity, and then in this case actually phi star or psi star, you can say that both is an isomorphism. So thus phi 1 x comma x0 is isomorphic to phi 1 y comma y0. Now is that clear? So if phi and psi are two maps in this way such that they are homotopic to this way identity, and this homotopy is base point preserving, then we see that this star equal to I star. We have seen that this is identity and this is also identity. So therefore phi star is an isomorphism. Why? Because they are identity, they are homeomorphism, right? So they are injective as well as surjective as well. So therefore they are isomorphism. And therefore we can say that pi 1 x with base point x0 is same as pi 1 y with base point y0. And in this case actually we say, this is the definition. So we say x and y, the topological space x and y are homotopic. Okay. So there was one concept homeomorphic. So what was the definition of homeomorphic? There will be a map from x to y and y to x, right? Which is, that is such that phi compose psi, right, equal to identity, and psi compose phi equal to identity, right? They are bijective. And here homotopic means we do not need, right? We do not need the bijective here, homotopic. Okay. So we just need that phi compose psi, it is homotopic to identity, and psi compose phi again it is homotopic to identity. So here we do not need those maps, phi and psi are bijective. Okay, so now this is the difference between them. So note that here. Or you can complete the sentence. Now if there exists phi from pi 1 x comma x0 to pi 1 y comma y0, not pi 1,
Sir,
this, and psi
sir,
y comma y0 to x comma x0. So there exists, you can say that maps this such that phi compose psi is homotopic to identity and psi compose phi is homotopic to identity. So note phi and psi need not be bisecting, and their composition may not be identity. Right? So they are homotopic to identity. And here, for a time being, we write this homotopy is base point preserving. That is the reason we mentioned here as well, that x comma x0 to y comma y0. Okay, so in
Sir,
that
here
in
we
that
are
case,
seeing X,
sorry,
space X and Y are homotopic. They are space, not map homotopic.
why I written that it is map?
No, sir. We in this definition we are saying that X and Y are homotopic. Are we talking about homotopic? Sir, in this
Oh,
definition
okay. Right. Yeah, we mentioned that only. Okay, we can write it two topological spaces x and y are homotopic. Okay, just a minute.
Sir, so like if we have a retraction map from X to its subset A, then X and A are homotopic. Can we say that?
Just say that you give the answer of that.
Yeah, like I feel that like they should be, but I wanted to confirm, like because if we have a deformation retraction from X to A, then like I star or R star uh, will be homotopically equivalent to identity on X, and R
Right.
star or I star will be homotopically like that is exactly identity on A.
Right. One part is exactly identity, and another one is homotopic to identity, and
So
it is
I
also base
star or
point
I
preserving.
star should be homotopically identity.
Right. So one is homotopic to identity, another map is directly identity.
Yes.
Right. So it satisfies the conditions. So therefore, it is an example. Now you can just recall the definition, and then you can find that. Now, if A is a deformation retract of X, then A and X are homotopic. Here your inclusion map and retraction map serve the purpose. Right? You can take one phi is retraction, another psi is just inclusion. Then you can see that there that is composition. One will be identity, another will be uh, uh, homotopic to identity. So therefore, that is a homotopic equivalence, right? So therefore, you can say that A and X both are homotopic. And if you make a homotopic, that means if two spaces are homotopic, then they have same fundamental groups. Okay. So
And are there other examples of homotopy between topological spaces, which is not retraction and which is not exactly homeomorphism also?
which one?
Like, are there any other examples except retraction and plain homeomorphism also? Like, homeomorphism will always be
Oh, okay,
special
okay,
case,
okay.
and
Right. No, there
retraction
are
is
many.
there.
There are right. There are many. There are many.
Okay.
There should be many. So what are the other examples? Which is because generally in topological purpose we generally do that retraction, but there are many. It is not necessary that that should be retraction, because retraction is also a special case, because one side is identity, strictly identity, right? But we can have homotopic to identity.
Even these two spaces x and y can be different. Say in retraction we had A is a proper subset of X, and in that case we had R and A are homotopic, and in this means that for this one homotopy equivalence case.
Aha, that is fine, but that is not a correct answer, Saurabh, because it is not necessary that you need a subset. Even that is right. So it is one sense, but that is not serve the purpose what he asked actually. So anyway, so Saurabh is saying that if you have say two topological space, when you take the deformation retraction, generally what is A? A is a subset of X, right? But now what you have when X and Y are topological spaces, right? They may be different. They may not be a one subset with other, but still they can be homotopy. But in that case, that is fine. Um, anyway, even it is not a subset, but still, if we can give another homeomorphism to a subspace, then it is looks like a diffeomorphism kind of thing only. But right. Can you have one quick example which is not deformation other than this, Sharon, which is not a deformation retraction but homotopic? Uh, there are many. I don't know why I'm not getting anyone. Okay. Anyway, just think about that. So there are many.
Sir, can we use that stereographic projection?
Stereographic projection.
From from S2 minus a single point with R2.
That is a homeomorphism.
Oh, okay, okay.
Okay. Anyway, so there should be many. There are many, but currently we are not getting any other example. Okay. So what we did here actually. So during all of this one, we choose that it is base point preserving. Okay. Now actually we can remove this condition, that is base point preserving, because we know that fundamental group of a path connected topological space does not depend on the base point, right? So therefore when we define homotopic, it should not depend on the path homotopy, right? Sorry, it should not depend on the base point as well, right? So that's mean what we want to remove the condition where it is. We want to remove this condition. Okay, now just define a homotopy of maps. Do not say that with base point preserving. So if there is a continuous map f x cross I to y such that only this condition holds. Okay, so there is no base point preserving. So homotopy of maps. Okay, so we are not saying that not base point preserving. So that's mean we say that phi 0 is homotopic to phi 1. Now again, you can say that why you are using the same notation, but anyway, this is understood, right? So we are just specifying here the cases, so not base point preserving, because we generally do not want to use more and more notations, because since all the things are basically same. Okay, so you are writing all the same one. So sometimes actually uh, people use when it is only homotopy, they use only this homotopy. When that is path homotopy, they use some kind of P here. And it is base point preserving homotopy, then also they use them another notations. But it is fine. It is fine to use only one. If you mention that during this we are only working on either base point preserving or not base point preserving any. Okay. So just fix and then uh, just go with the same notation. So we say that phi 0 is homotopic to phi 1, obviously not base point preserving. If so, there exists a, okay, we do not write it is continuous function, or you can just write it as map. So if x cross I to y such that f of x comma 0, it is only phi 0, and it is x comma 1 is only phi 1. Okay, now phi 0 is homotopic to phi 1. Now then, what will be phi 0 star and phi 1 star? What will be that? Now can you say that these are equal? What is your guess? Yes, what is your guess? Yes or no? I am not asking for answer. I'm asking for your guess. So what should be? Yes or no?
Yes, it is. Yes, of course.
Actually, it is not true. It is. So okay, I should write here x and y are path connected. But right. So why this is not true? Okay. Now what
Like
is
if you
your,
have like if phi 0 star will act on some function, then and phi 1 star will act on the same function, then they can change the base point, so like they won't map them to the same output.
exactly. So
The
that's
base
mean
point will
what,
be different, but they might be isomorphic or something. uh,
eh, right, but they
but
are isomorphic, obviously isomorphic, right? But we cannot write they are equal, right?
right,
So
right, yeah.
huh. So we will prove that only. So that is the reason when we are talking about that isomorphism, we generally do not consider the base point. So that is the reason when we define homotopy map with base point preserving and we do the same thing, right? And now we will show that everything will be true if we assume that it is not base point preserving as well, because we have already proved that fundamental group of a topological space, path connected topological space, does not depend on the base point. Right. First of all, why this is not true? Because what is your phi 0 star? Now phi0 star is a map from phi1 x, say from x0 to phi1 x comma phi0 x0, right? Sorry, y. So this is a map from this to this. Now what is your phi1 star? It is a map from y comma some phi1 x0, right? Now see that now the codomain of this and this are different. So right, they are different because we do not know that phi0 of x0 is may not be equal to phi1 of x0. So we do not know this one. This is equal or not. Right. So in general, we have to assume that they are may not be equal. So in fact, it is not equal. You can say that. So therefore, their domain are different. Codomain are different. Now, since their codomain are different, so therefore we should not say that they are equal. Okay. Then what it is? Then what it is? Now, obviously, you can now check that. Now, what is actually? Now you can guess actually. Now this is your pi1 x comma x0. This is your pi1 y comma pi0 x0. This is your pi1 y comma phi1 x0. Now you have this situation. You have this, and you have this. Okay. Now this is your phi0 star. Okay. And this is your phi1 star. And what is this? This to this or this to this? Anyway, both are fine, but I forgot. Do you remember that map, that beta H?
It's HF H bar, HF H inverse.
H, F, H inverse, right?
Uh,
And what was the H?
H was path from x0 to x1. So if you have a loop f based at x1, then hf h bar will be a loop based at x0. So it will map loops based at x1 to maps at x0.
So it is phi 0 x0 to phi 1 x1. Now say suppose this is my map H, and then it goes to where to at this angle dot or this angle. So first we take H. Right, it goes to this direction. Am I right? Right, right. Because first we take any element which with base point this one, then it goes to H. That's mean from this to this, and then we have a loop, and then this. Fine. Now this is a loop. Now therefore, it is actually you have to prove that. Oops. So you have to prove that now phi 0 star is actually beta H compass phi 1 star. This. So this to this is same as this to this. Right? Is that clear to everyone?
No,
We
sir.
will we will prove that. No, from the figure, is it not clear from where it goes to maps to? So did you get what is your 50 star from this to this map? From this space to this space? 50 star. Is that clear?
Yes.
Okay, this is clear. Now what about this one? Is that clear? This? So therefore we have this figure.
Yes, sir.
Okay. So now what we will prove actually? Now we have to prove that. So that is our guess. So what will it should be? Now we will prove that. So now let first of all h of t equal to phi of t x0. So that's mean h is a path from phi 0 x0 to phi 1 x0. Okay, see here I have written that h. Okay, right. Now with this h you can define a map from this space to this space. Now define. We have already seen when we prove that fundamental groups are not base point preserving. We proved that. Then in that case, then beta h is a map from pi 1 y pi 1 x0 to pi 1 y comma phi 0 x0 in the sense that beta h of say f, when you have taken a loop, it is actually h dot f dot h bar. This one. So that's mean, say this is your phi 1 x1 and this is your phi 0 x0. Okay, and say this is your loop. Say this is your loop h. Sorry, path h from this to this. Now what is the case? Now what is f? F is a loop from phi 1 x0. It is a loop from phi 1 x0. So suppose this is a loop in phi 1 x0 with base point phi 1 x0. Okay. Now what is this loop? This loop is from h. See, now its base point is phi 0 x0. Why? We go from phi 0 x0 to phi 1 x0 by the map h. Right? We go this direction and we have a round here. This is a loop, right? And then again we go back here in this direction. So we stop here again. Right? So this is a loop in this. Now we have seen that this is an isomorphism. We have seen that. Okay. Now up to this, is it clear? Yes. So if you have any problem, you should ask. Is that clear? I am asking. No one is giving any answer.
Yes, sir. Like it's clear to me.
Good. Okay. Now this is an isomorphism. Now what we need to prove that we will prove this. So this is homotopic to this. Okay. So this is same as this. So first of all, we will actually prove that phi 0 is homotopic to beta, that is okay. So you will see that what it should be. Okay, fine. Right. Now this is your path. So now we just change the notation. Notation means we just replace t by s. So now let hs is the path from 50x0 to 51x0. That's when we just replace t by s. Okay, because we need t, so we should not write here t. Okay, now let we define a map h of t s by h of ts. In this way we define another path. Now what is your then a0 of s? What is a0 of x s? If you put t equal to 0, that's mean it is h0.
Constant
H of, right.
e sub 50x0.
No, this is just a point, so it is just this. Right. Okay, in that case, okay, I am writing, right.
We had that e symbol na for identity earlier. So
Means I will use that. That means a0 is equal to this. So we can say that a0 is your e50x0. Okay. I am asking about one point only, na? Yes.
yes, right.
Okay. So it is a single point. If we write a0, that's mean we are writing in this symbol. That is not h0s, it is h0. This. Now what is my h1s? Now h1s means now you can see that it is h of s. So that's mean h1 equal to just h. Okay. Right. Now what we can define now. Now then if we define ht dot phi t phi t s no phi t f dot h t this. Okay, now why this is well defined, we have to check first. What? Right, we can just check here. Now what is my ht1 equal to h of actually t? What is my h of t?
Phi t x0.
Ah, right. So it is phi t, oops, x0, right. So this is phi t x0. And what is my phi t f0? That is my phi t f of 0, and f of 0 means again x0, right? Why? What is my f?
Like f0 is x0, so phi t f0 will be phi t x0 again.
No, I'm now getting confused. What I'm doing here?
So
To
f was a loop based at x0. So f0 is x0
No,
only.
actually, F was a loop from pi 1 x0.
right.
Right, pi 1, yeah, so it was based at x0. Uh, okay,
No,
here,
no, no.
actually,
So that is phi 1 x0. Because of that replacing, I think I made the mistake. Okay, anyway. So first of all, what is that? It is phi. No, it should not be, but I think there is some problem. Phi compose F. What do you mean by phi TF then? Okay.
like for every t, phi t should be a map from x to y, and uh, yeah, phi t always goes from x to y. So yeah, phi t f0 is well defined. It's equal
No,
to
I
phi
am
t f0.
just a minute. I am little bit confused here. So we need this kind of path at the point T. So H1, HT1, right, HT1, it should be some phi T x0. Now that is fine. Okay, fine. Now here we need a function that should be phi T what? Now we need this loop actually. So what is that loop? What is that loop?
Yeah, I think phi t f should work because f was a loop based at x0, and phi t maps the topological space capital X to topological space capital Y, where base point x0 goes to the base point phi t x0. So phi t f will be a loop in Y with base point phi t x0.
Actually, the way I have defined here, so just a minute. Phi t. So what is phi t? Okay, actually, right. So I should not see this one. What is phi t? Ha, great, great. Yeah, right, right, right. I am giving that notation because this one, just we have to forget this stuff actually. Because of same f, I am getting confused, right? So what was actually my phi? So come from this one. So what is my phi? Now what is my phi 0 actually? Now phi 0 star is a map from pi 1 x comma x0 to pi 1 that is y comma phi 0, right? So that's mean phi t star, right? Yeah, good one. So that will be f because phi t is a map from pi 1 x comma x0 to pi 1 x comma phi t x0. So
Y,
this.
pi 1 y.
Oh, sorry, sorry. So this is not pi. So that's mean phi t star is a map from pi 1 x comma x0 to pi 1. Oh, this is y comma phi t x0. Right. So now if we take a loop this one f, for any loop this, we have phi t star f equal to phi t compose f. Okay, now we have this phi t actually. Okay. Now this is well defined. Okay, now phi t f 0 equal to phi t f of 0. So that is phi t x0. So this. So what we are doing this? So right. So this is my situation. Okay. So we can draw again the figure. Right. This. So therefore you can say that a0 dot phi 1 f, sorry, phi 0 f dot h0 bar is homotopic to h0 h1, sorry, phi 1 f dot h1 bar via this homotopic because that is continuous. Now and we'll define phi tf ht bar, this one. Now what is this map? Now what is this one? Now we have find that one, right? What is my h0? Now h0 is just identity and h1 is h, right? So h0 is identity. So that's when it is phi 0f is homotopic to. Now what is my h1? H1 means h, right? So h dot phi 1f dot h bar. And this is okay, this. So now phi 0 star
Sir,
f, yes.
can you explain the previous step? Like after that, how homotopy? How can we write phi phi compose f is homotopic to h phi 1 f?
Because h0 is identity.
Okay.
H0 is identity and h1 means h. We have proved that. See, h0 is identity and h1 means h. That way we have defined that h. Okay. See, now what is this one? Now this one is phi naught f, and by this homotopic we have proved that that is h naught phi 1 f dot h bar, and that is actually beta h phi 1 f, and that is actually beta h phi 1 star h f. So this is true. So this is true for all h belongs to pi 1 x comma x0. So therefore pi 0 star is equal to beta h pi 1 star. Okay.
So for all f.
Ah, thanks. Okay, now we have proved that. That is very simple. I made it complicated by introducing this one. Now I got confused here actually. So here I use the same f And then when I was writing here, I got confused with that app. I thought this app is same as this app. This is not actually. Okay. So what is actually the thing geometrically? So you should understand that. Okay. So what is actually? So this is my x and this is my say y. Okay. And say this is my x0 and say this is my phi 0 x0. Okay. And since we have that phi is homotopic to phi 1, so that is my phi 1 x0. Okay, so we have two maps, right? Phi 0 and phi 1. Now this is my x0. So this is my phi 0 x0 and this is my phi 1 x1. Now since we have a homotopy phi t, say that homotopy is a, if you consider that homotopy at exactly 1 points, then it will be a path, right? Because t varies from 0 to 1. Say this is this path. Okay, so this path is actually your phi t x0. Okay, so this. Now, whenever you have a loop, so this is my loop, so that was my f. Okay, so this loop is actually here this one, this loop is this one, and this loop is here this one. So under the map phi we will get this, under the map phi 1 we will get this one. So this is actually your so phi 1 f and this is actually your phi 0 f. Right now what we will prove that actually we will prove that this phi 0 f and this phi 1 f are homotopic in some sense by the map B. Now if we consider that is your beta, right, then we actually prove that this map is homotopic to this. Okay, so we prove that this phi 0 f is homotopic to that this one. So H beta H that phi 1 f H bar. Okay, so we prove that phi 0 f means this loop only, this loop, and phi 1 is this means. So first go to this, take a round and then come back. We prove that this is homotopic to this. So this loop is homotopic to another loop. Now they both have same base point. They are now path. So they are now path. So you can talk about path homotopy, right? Because now say because of this f, my domain is now 0, 1. Now we prove that they are same path homotopy. Since they are path. Now how to prove that? Now we define in HT in some sense. So we define that HT dot phi tf dot HT bar. So in this way we prove that this is homotopic to this via this. That's mean at the point 0 it is this. So at the point sum it will be goes, it will be like this way. So from start from this point go this, then have a round and then come back. And then after some stage it will gonna go this, round this and then again come back. And similarly, so this is first step 0 and this is a 1 by 4th, this is a 3 by 4th and this is 1. So in this way actually they have the homotopy. Now we got this geometrically as well.
ज्योमेट्रिकली फिर से बता दीजिए.
Okay. So anyway, you have recorded video. So now you can just go through that one. So what I'm saying that, so when you have this loop, now this loop goes to this loop by phi 0 and this loop goes to phi 1. Okay. Now this loop has two images. By the map phi 0 it is the lower one. By the map phi 1 it is phi 0 it is lower one. By the map phi 1 it is the upper one. Now we show that phi 0 f, this is a loop, and this is also a loop, and with the same base point, that phi 0 x 0, the same base point. Now we prove that this and this two are path homotopy. And what path homotopy we choose? Now this is my path homotopy. So what is that path homotopy? At the point 0, at the point t equal to 0, it is this loop only. When t equal to say 1 by 4, it goes 1 by 4 distance here and take a round and come back, right? 1 by 4 distance, take a round and come back. When it is say 3 by 4 time, it go this, take a round, then come back. And when it is 1, it goes this, take a round, then come
Yes,
back.
sir. Got it.
Okay. Now since
Yes.
X is path homotopy, we have proved that these are actually homotopy of paths because this is continuous. So therefore this homotopic to this, and since this homotopic to this, so we are done. So now so this will imply actually, so phi 0 star is same as say beta h phi 1 star. Now this imply this. Okay. Now by, so we have proved that, right? So this. Okay. Now we actually prove that. Now if x and y, two topological space, are homotopic, so homotopic means here we are saying that without that base point preserving. Okay, now then pi 1x is isomorphic to pi 1y. Okay, now still this is true. Now previously we proved that if they are homotopic with base point preserving, then their fundamental groups are same, that is isomorphic. Now we prove that if they are even only homotopic without base point preserving, this the statement is true. Okay.
So we are assuming that they are path connected.
Right. It should be. It should be. But that's mean everywhere in this algebraic topology course, we always assume that if it is not mentioned, you should assume that x and y are path connected. Because if you do not assume that it is path connected, then fundamental group will not be unique. Depending on base point, it may change, but we don't want that. Okay. Now what was the situation? So since it is homotopic, that's mean so there exists phi from pi 1, say this, and there exists psi such that phi star, say compose, so not phi star, so phi compose psi, that is homotopic to identity. Again psi compose phi, this is homotopic to identity. Now note that it is not base point preserved. Now what is this phi and psi? Now we draw this figure. Now first of all fix a x0 in x. Okay, so therefore my x comma x0, it will be y comma phi of x0. Now if you take again psi, it will be x comma psi phi x0, and if you again take phi, it will be y phi psi phi x0. It will be this one only. Okay, and that's mean psi compose phi. So this to this, it is homotopic to identity. So identity means identity in X, right? So therefore, psi star compose phi star. Now what is that? We proved that. That is previously we proved that. So that's been we have pi1 x comma x0 to pi1 x comma that's phi x0. So that is your psi star phi star, right? And we know that there is another map from this to this by the base point preserving. No, not this way, in the reverse direction. Beta h, right? So therefore, anyway, that is isomorphism. We don't have to bother about that. By taking that part, that is fine. So equal to say some beta h, right? So it is beta h composition identity star, that is identity. So it will be this one, right? Now we know that beta h is an isomorphism. Right now, since this is isomorphism, so phi star is injective. That is just trivial, right? Because if you take phi star f some equal to say phi star g, just apply again psi star. Since it is isomorphism, then you will get it is injective. Okay. Now again, similarly, so phi star compose psi star, it will be some beta, say some h dash. Again, this is an isomorphism. So therefore, so thus psi star is injective, right? So therefore, you have psi star and phi star. Okay, both are injective, and psi star compose phi star is isomorphism. Thus, you can check that phi star is surjective as well. So that's when it is in this way actually. So pi1 x comma x0, pi1 y comma y0. Sorry. Now pi1 x comma. So this is phi star. So this is psi star. Psi compose phi x0. Okay. Now say this map. Suppose this is my say beta h. Okay. Now. Okay. Now what you have? Phi star is injective. Psi star is injective. And beta h is a isomorphism. Now we have to show that phi star is surjective. Now this is simple. Now take this is a G. Okay. Now this G goes to here psi star G, and you take that preimage. Now this goes to this. Now this goes to here say beta H in, but since it is isomorphism, psi star G. Now you can check that this again goes to this because of this injective. So that's when you can check the 5 star of this one will be G. Therefore, G is also 5 star is also in surjective. So therefore, 5 star is 1 1 on 2 and homomorphism. So therefore, 5 star is isomorphism. So thus we can say that if two spaces are homotopic, we don't care about it is base point preserving or not. We always have pi 1 of x is same as pi 1 of y. Okay, so we are done. So in the next lecture, so we will talk about that Van Compen theorem. So I will not go through that details proof of Van Compen theorem, because if I prove that precise statement of Van Compen theorem, then it will take 2 lectures at least. So I think it is better to not spend that many times actually for single lectures, but I will give you the idea. So I will give you a idea of that one. So I will give the outline, but I will not give that exact proof of that one. But that rough idea is fine, because whenever you are reading a big theorem, which is a big theorem, so there is no meaning of actually once you read, obviously once you read, but anyway you do not remember the proof. But if you have that idea and if you have the outline, then that will be definitely will stay in your mind. So I will give you the idea and what is the logic behind all of this. So I will just quickly go through that outline of the proof of the Van Compen theorem, and I will see some application. Okay, so in the next lecture we will see some applications as well. So anyway, so any question?